Record. I just hit the record button and let's go to the board. Board looks good. And maybe there is a glare, so I'm gonna close the window. Let's talk about aromatic compounds. It's a beautiful day. Hard to be inside. A little chilly, but then it's kind of looks kind of fun day to me. All right, let's talk about some chemistry. So this is Chem8. Chem8, what else? Chem8, Tuesday, Thursday, fall 20, and today is 11/19/20. Aromatic compounds. If the camera is off focus, let me know. Okay, we're talking about
It's off.
aromatic. Bad. Oh, darn it. Yesterday it was really problematic. I hope today is not that bad. Okay, we'll check maybe in a minute or so. Aromatic compounds. Okay, and we briefly discussed how as you put double bonds in a cyclohexane ring, if you put double bonds in a straight chain hexane, hexane, hexene, hexadiene, hexatriene, right? So when you go from hexane, no double bonds, just single bonds, all sp3, to hexene, one double bond, the energy goes up by some amount. You stick a second double bond, the energy goes up by approximately the same amount. You stick a third double bond, energy goes up by the same amount, approximately. So the bottom line is the point I'm trying to send across. The point I'm trying to send across is that for adding a double bond, you are making that molecule uncomfortable, unstable. And that amount of instability is increasing by the same amount as you keep adding more and more and more double bond. One double bond, second double bond, third double bond. If you do fourth double bond and fifth double bond, if you have a long enough molecule, it'll keep going up by approximately the same amount of energy. But in a cyclic system, in a hexagon, cyclohexane, hexagon type of a system, as you start sticking double bonds, stuffing it with double bonds, things get a little hairy at the end. That's where the concept of aromatic compounds come in. That's where the first aromatic compound ever, not invented, ever discovered by chemists, benzene, that comes about. Okay, so let's discuss this. So we have energy. So higher up means more energy, lower down means less energy, right? So let's start here. Cyclohexane. Let's say its energy is here, okay, in the middle. Now, as we put one double bond.
Larry, Professor.
Okay, thank you. I need to solve, I should have solved this problem, but I have tried, but it hasn't really gotten any better. Let me just go back to the video setting one more time and undo the HD and redo the HD. Let's see what happens. Maybe this will help. Kind of like resetting the whole thing. Okay. So no double bonds, one double bond, and let's say this gap is delta E. Okay, the energy of this guy versus this guy is whatever, some amount. Okay, now we stick a second double bond. let's make that second double bond look. I think I used the blue color. And again, that gap is delta E, okay? As you're sticking the first double bond, it goes up. Second double bond goes up, same amount, same gap, okay? Now, funny things start happening once you put a third double bond. Once you put a third double bond, the molecule behaves very differently. You expect, this is what you expect. This number, this is expected. You expect it to be going up by so much energy. In reality, it has been found that that amount of energy that you expect it to be unstable with, that's wrong, okay? So this number has turned out to be, even though it is expected based on your, previous observations and other data, this number is wrong. It's not here. This is the wrong level. The real level is slightly below, okay? This is where you expect this molecule to be. Expected. Apparently, that level, that energy level is wrong. The real energy level is slightly less. Sometimes going through this color can be pretty time consuming. I probably spend more time changing pens while I'm lecturing. So let's say this gap is here. So this is, okay, this is real. This energy level, let's say this is from here to here. I don't know the number. Let's say that gap is, it's supposed to be delta E, right? But let's say it's not delta E, it's delta E prime. So delta E prime is a smaller number than delta E. It's supposed to be going up by, if this is a pen length, it's supposed to be going up by that much, oops, that much and that much and that much. But in real life, it's actually less than this. It's this much, okay? So that gap, it's supposed to go up by so much. I'm unstable today. It's supposed to go up by so much, but it actually goes up by this much. That means it's stable. It's stable for some unknown reasons. We don't know exactly what that unknown reasons are. So this gap, green minus purple. So delta E, there is no math, so relax. No need to worry. Delta E minus delta E prime. This is the weird stability, okay? That we have no idea why this setup makes the molecule more stable than what you expect it to be. You expect it to be very jumpy and unstable and reactive, but in reality, it's not. So in reality, this gap is unprecedented stability. This is the strange stability of this molecule that was not known before this particular molecule was first identified. If you look at the molecule, this molecule is weird, okay? If we call it cyclohexane, we talked about it. Remember, for the final is cumulative, and you need to know pretty much everything we discussed in this class. That guy is cyclohexane. Remember, we talked about cyclopropane. flat molecule, cyclobutane, a flat molecule, cyclopentane, like an envelope, cyclohexane, like a chair, right? Like a beach chair with a backrest and a footrest. And the backrest and the footrest, they can flip up and down and become another chair. The backrest can become footrest, and the footrest can become backrest, and they can become a different chair facing the other direction. Okay, we talked about it. Just make sure you understand. You haven't forgotten stuff. You need to know everything when you show up for the final. Cyclohexane, we will call this guy cyclohexene. This molecule, you don't have to know the name, but I'm just going to write it down. It's called cyclohexadiene. Okay, 1, 3, 1, 2, 3, 4. 1, 3 cyclohexadiene. So ideally, we should name this guy 135. 1, 2, 3, 4, 5, 6. Double bond, red double bond starts here, 1. Blue double bond starts 3. And green double bond starts at 5. So it should be called 135 cyclohexatriene. If this was nothing but an alkene, if this was one of those alkenes that roam around on the straight corners, then we would have called it 135 cyclohexatriene, like this guy. Again, this is not needed for your quiz or exam or whatever, your final. I'm just saying it because I think some of you might want to know. If it was nothing special, but you already saw that there is something weird and something special about this molecule. It's supposed to be unstable, but it's got some funny stability business going on in this molecule, which was not known until they first identified this compound and discovered this compound. Okay, so this name was rejected. This is not the right name because it's not just an ene, it's not just an alkene, it's more than that. It's more stable than an alkene. So this molecule is called, who knows what it's called? It's a B word. Cyclohexane with 3 double bonds. What is it called? You know, come on. What is it called? BEN? No?
Benzone, something like that.
Benzene. It's called benzene. Okay, this is called benzene, and it was the first aromatic compound ever, not invented. We don't invent molecules, first identified. Okay, this is the first aromatic compound. Okay, this compound was not, its structure wasn't known, and if you look at the molecule and if you look at its exact structure, this is what it looks like. Single bond, single bond, single bond, single bond, single bond, single bond, double bond, pi bond. That's another pi bond. That's another pi bond. Okay, and then on top of that, you got 6 hydrogens. Because this is sp2, all of them are sp2, all of them are flat, and this is what the molecule looks like. Okay, C6H6, C6H6. That's the formula. This was found as a liquid distillate from petroleum. Most of the things are basically petroleum products. The plastic, the whatever glass you have here, some of the synthetic materials, polymers, different solvents, glue. What else can I think about? Not paper. Paper comes from trees, right? That's bioproduct. So much, like the plastic that's used on switchboards, that's different kind of plastic. Other chemicals, and chemicals are used to make molecules. So different chemical products, ammonia, ammonium hydroxide, toluene, benzene. This guy itself, it was used as a commercial thing. And that was a bad idea. We'll talk about that maybe briefly. We don't have a lot of time for storytelling. So this came from, all this stuff comes from the petroleum that we get by going in the crater of the earth, right? We dig out the petroleum, we distill the petroleum. It's pretty dirty to begin with. At different temperatures, different things boil out. And this guy, C6H6, came from petroleum. Some, whatever temperature, I don't remember benzene's boiling point, I think 70 something degrees. I don't remember exactly what it is. This guy came from petroleum, and it was C6H6, and it was acting really weird. The normal hexane, what's the formula of normal hexane? C6H14. When you have no double bonds, no triple bonds, completely saturated, that means it cannot take any more hydrogens. That formula is C6H14. 14 minus 6, what's that number? 8. So it's missing 8 hydrogens. 8 hydrogens are missing. Okay, 8 hydrogens are missing, 2 hydrogens per double bond, right? Or when you ring it, it's got, when you cyclize it, you also lose 2 hydrogens. So 8 means 8 hydrogens missing means there is a lot of unsaturation. There are a bunch of double bonds or triple bonds in the beginning. I think the debate for the structure of benzene went on for a long period of time, until someone named, a scientist, a chemist named Kekulé, cracked the code. He had apparently had a dream. He was seeing snakes, and the snake was acting like a dog. Maybe it was a dog in its previous life. And the snake in Kekulé's nightmare, I think it cannot be a dream. I don't like snakes. So if there is a snake lover, forgive me. I don't like snakes, okay? I grew up with cobras in our neighborhood, and we were scared of dying from cobra bites, okay? So I'm not a big fan of snakes. If you have a snake in your house, you'll be happy, but I'll never visit you. So Kekulé apparently had a snake dream or a nightmare where the snake was chasing its own tail, thinking like, maybe it grew up with dogs. And eventually it bit its own tail and formed a cycle. And this structure elucidation, like finding out what does this weird C6H6 guy look like, was going on for like decades. I don't know exactly what the history is. So Kekulé was bothered by it, and he had a nightmare, and he saw the snake catching its own tail. He saw the cycle, and he woke up, and I don't know if he said eureka. He apparently figured it out. He said, I think benzene, this molecule, is cyclic, and this is what it looks like. So there is if you ask any chemist, he or she will tell you the story of snakes attached with the discovery of the shape of benzene, okay? So this is what it looks like a snake, okay? Double bond, that means that, and that. The end of the double bond and the 4 other things the double bonds are attached to are planar. Remember, this is all sp2. Just remember that, it's important. They are all sp2, hybridization. sp2, 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 sp2. Okay, they're all sp2. The bond angles are roughly 120 degrees, approximately. This bond angle is approximately 120 degrees. All the bond angles are approximately 120 degrees. The entire molecule is flat, like a frisbee. If if you think about it like a little sheet, like a hexagonal sheet with the hydrogens popping out from each of the hexagonal corners, it's really paper thin. Benzene is thin, exactly like that. All the carbons, carbon, 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 and the hydrogens, they're all on the same plane. This molecule is really incredible shape. Okay, so this is what it looks like. So that's the discussion. Now let's see why. Well, we're not going to discuss why benzene has less energy, but this is the first aromatic molecule that was discovered and or identified, and people started realizing that this guy, even though it has double bonds, even though it has a cyclic structure, it doesn't behave like a normal alkene. We'll talk about that, and we will talk about the rules of aromaticity. We'll talk about some reactions of aromatic compounds, and we're going to talk about some naming of aromatic compounds, and that will pretty much, end our discussion today. Okay. So while I prepare to take a snapshot of the board, you guys stare at the board and make sure that this is making sense. It's important for Tuesday's exam. Okay. This is kind of like the history of aromatic compounds. Okay. I'm going to erase. So let's erase the board and talk about benzene and other aromatic molecules. Like, what do you have to look out for a compound to be aromatic? What are the requirements? Can it be a straight chain compound? Does it have to be cyclic? Does it must have double bonds? How many double bonds? Can you not have a double bond in the middle and still be aromatic? Can you have something else in there? How many double bonds? Can anything cyclic and double bonds will be aromatic? So we will investigate these aspects now. So on the right-hand side, what I'm going to do is I'm going to write down the aromatic rules. And on the left side, we're going to start kind of like messing with the molecules, like analyzing different types of shapes and different types of compounds and see if they're aromatic or not. So what does it take for a molecule to be aromatic? Okay, I'm going to draw this molecule benzene, maybe a little bit smaller on the left side, and I'm going to discuss the rules on the right side using different colors. My wife has already scolded me for using too much color, like in the same sentence. She said it can be confusing for your students. So do not change color while you're writing a same sentence. I said, okay, I will listen to the suggestion. That makes sense. I don't want to overdo anything. I have criticized heavily in the past when a Nobel laureate actually gave a talk, and I said that the presentation was really bad because it was just too colorful. There was too much color. And it sounded like, like a bad artist's bad painting. So I criticized them. And of course, my friends did not appreciate it because he's a really famous chemist. His name is Kesey Nicolau. He's at Scripps Institution in San Diego. And he likes to put too much on slides and too many colors. So I thought that maybe I'm doing the same thing. So I should slow down and back off a little bit. Okay, so on the right side, let's put it in black. Rules of aromaticity. Okay, rules of aromaticity. This is important. Okay, now obviously, if we have hexane, it's not aromatic. I'm going to just put like a cross, not aromatic. Hexene, it's not aromatic. If we have two double bonds, not aromatic. If you have three double bonds, it's not aromatic. If we have cyclohexane, it's not aromatic. If we have cyclohexene, it's not aromatic. If we have cyclohexadiene, it's not aromatic. It's aromatic when you first, what you have seen so far. If we have a situation like this, it's aromatic. Okay, time for celebration. Not, yes. Okay, so rule number one. What should be rule number one? Anybody? What should be rule number one? The snake must bite its tail.
Is it must be a cyclohexane? Or-
Cyclic. Must be a cyclic molecule. Right thinking. Must be cyclic. This is cyclic, this is cyclic, this is cyclic, this is also cyclic. That's not, this is yes. So what should be rule number two? What does that cyclic shape have?
Three double bonds.
For this case, alternating double bonds, double, single, double, single, double, single. Okay, good idea. Thank you. Alternating double bonds. Okay, can this work? I'm just going to tell you that it doesn't work, okay, because you don't know yet. Can something like this work? Alternating double bond, but there is a little problem here. The alternating double bond is like two single bonds here. You can think about that it's not alternating double bond, or you can think about it the way I describe it. It's very colloquial and very crude way of describing it, but it might stick to your system better. I call it, see, this is a pi bond. That's a pi bond. This down here, it's sigma, 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 sigma. They're all sigma. Sigma is a bad idea. If you have all sigma, okay, not good. And I call it, I have given it a name. I call it a sigma wall. It's kind of like a sigma wall. The electrons cannot jump around, okay? So this is a sigma wall. So alternating double bonds must be there. This means the alternating double bonds is not really happening here. Or you can think about, I'll just write it down in a parenthesis, no sigma wall. Okay? No sigma wall, but what if you have a situation like this? What if you have two double bonds, that's alternating. Down here, you don't have a sigma wall, but what you actually have is a negative charge. Or you have a situation where you have a positive charge. You have nothing. This carbon has no electron whatsoever. So it's positive charge, it's negative charge. Or it can have something with a lone pair, like a nitrogen with a lone pair. What about that? Okay. I'm just making sure that you guys are following the Lewis dot structure and not getting confused. Carbon is born with 4 electrons. It's got all 4 electrons here, so it's neutral. You remove this hydrogen, leaving its electron here, then you get a negative charge. You remove this whole thing with the electron that came from carbon, and then you get a carbocation. This is a carbocation. This is a carbanion. We talked about it in the past, recent past. This is a nitrogen. It is looking like that guy, but nitrogen is born with an extra electron. So it's not negative. That's how electrons are, nitrogen is born. It's got the right number of protons. So this is neutral. So the next rule says that sigma wall is a bad idea, but it's okay. It may be okay to have a negative charge or a positive charge or a lone pair. Okay. Maybe, I'm just going to say maybe because there is another rule. Maybe okay to have negative or positive charge or lone pair or lone pairs. One or two lone pairs, because nitrogen will have one lone pair, oxygen will have two lone pairs. If you have a molecule that has an oxygen here, like water, this guy has not one, but two lone pairs. Okay, so this may be okay too. This may be aromatic. We don't know that yet. Okay. So rule number one, must be cyclic. The dog must have bitten its tail, its own tail, not somebody else's tail. Remember that. Number two, you must have alternating double bond. This is a perfect example of alternating double bond. This is a bad idea. Not good. There is no alternating double bond, or you can say there is a sigma wall. Sigma wall, bad idea. Well, sigma wall is a bad idea, but can you have a positive charge or a negative charge or a lone pair or bunch of lone pairs, two lone pairs? It may be okay. These are the three rules, the important rules. Last rule, very important. Last rule says number of pi electrons. Number of pi electrons that includes lone pair, that also includes negative charge. I'm going to write it down in a different, well, my wife told me not to change colors. Okay, black. Number of pi electrons, including, I'm just going to say negative this way, okay? Trying to save space. That means negative. Negative charge or lone pair, LP, not long playing vinyl records, LP lone pairs. Number of pi electrons, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, nothing. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. You count the negative charge on the negative on the anion. 5, 6. 1, 2, 3, 4, 5, 6. You don't count two lone pairs. You just count one. We will talk about that in a second. Okay. So the total number of pi electrons, whatever that number is, 2, 4, 6, 8, 10, 14, something like that. Whatever the number is, that number must be written as a formula. That must be written as 4n plus 2 as a formula. I'll explain it to you. No need to worry about it too much. So these are the rules of aromaticity. Okay. It doesn't make sense at this point unless we do some practice, unless we go through some examples. So once we go through some examples, the rules will start to make more sense to you guys. Okay. So I'm going to take a picture and I'm going to just erase this part and keep that, the rules, and then start investigating a bunch of different compounds. It'll make sense. Number one, take a picture. Number two, erase. Number three, I don't know what number three. Okay, Okay, I took a picture. Just take a look at it for a second. Not aromatic, not aromatic, not aromatic, not aromatic, must be cyclic, but cyclic doesn't cut it. You must have double bond. One or two doesn't work. This is not, alternating double bond. You must have alternating double bond. This is not alternating double bond. There is, you can say the same problem in a different way. It's got sigma wall, okay? This guy doesn't really have a sigma wall because it's got an empty p orbital. So I already told you in rule number 3, positive charge may be okay. We don't know. Negative charge may be okay. Having a lone pair or 2 lone pairs may be okay. Why? Maybe because you still have to count the total number of electrons and make sure that you can write it as 4n plus 2, okay? Where n, we will discuss that now. Once I erase it, n has to be a whole integer, W-H-O-L-E, not H-O-L-E, not whole, okay? W-H-O-L-E, like a complete integer, not a fraction. We'll talk about that now. So what does the, I think the last rule sometimes causes confusion, and I want to make sure that you guys understand it very well. Okay, so the last rule, it's called Huckel's rule of 4n plus 2, but you don't have to know that name Huckel. I'm just trying to like drop as less number of names as possible. So the rule is 4n plus 2. We'll get there in a second. Okay, so let me just draw a molecule and ask you, like, is this aromatic? Is this aromatic? Yes or no? Check those boxes and tell me. Don't go through all the rules if one rule just tells you that this is not aromatic because of the simple reason. Is this aromatic or not? Speak up. I'm not.
No.
Okay, why not? Give me one good
cyclic.
reason. Sorry, not cyclic.
Cyclic.
Yeah, not cyclic. Absolutely. Okay. This is cyclic. Aromatic? Hurry up. Please, hurry up. Is cyclohexane aromatic? Cyclic.
No, it doesn't have alternating.
It doesn't have
double.
alternating double bond, right? Okay. So now let's go through this. Aromatic.
The board is super blurry.
Board is blurry. Yeah, it is blurry. Okay, there you go. Okay, autocorrect. Board has the camera has its own mind. Obviously, if I get out of the screen, it's okay. I'm going to stand here. I'm going to stick myself to the board. Okay, hopefully it's focusing now. Aromatic. We just discussed it. That rule does it. Yes or no? Quick, quick, quick. What's the problem? Or you can think about that. There is a problem here. What is that problem?
It has a sigma wall.
It's got a sigma wall, or it doesn't have alternating double bonds. Alternating double bond means double, single, double, double, single, single. That's not good. Okay, so this is a problem. So it's not aromatic. Now, aromatic. What do you guys think? Now we need to learned something about that rule. Number of pi electrons must be written as 4n plus 2. Okay? Where n is 0, 1, 2, 3, 5,000, 10 million. I have no idea what it is. Any number, any whole number, not half, 3/4, 5, 6. These are forbidden. That doesn't work. Whole integer, okay? It's not calculus. It's simple math. You can do it. Okay. How many pi electrons does this molecule have? Tell me. How many pi electrons does that box molecule have? Cyclobutadiene. How many? How do you count it? How many pi bonds? How many electrons in the pi bond? And then how many pi bonds? Then do the math. How many labile or pi electrons are present in this molecule? Quick. If you stumble here, it's not going to be pleasant on Tuesday. I'm not threatening you. I'm just saying that I'm just trying to prepare you. How many?
4.
Thank you. Okay, the point here is, can you write 4 as 4n plus 2? One of my students actually showed me that instead of trying to explain it, why don't you ask your students, ask us to solve it and see what the number for n turns out to be. Solve this equation, okay? So 4n equal to 4 minus 2. You can do that. It's not complicated math. Don't tell me that. So take 2 on this side, it becomes negative. So 4n becomes 2. That means n equals 2 over 4 half. N's value is turning out to be half. Not good. This doesn't cut it. N must be a whole integer, not aromatic. Got it? Let's analyze another molecule. Benzene, you know it's aromatic. Now let's go through the rules. Rule number 1, cyclic. Check. Alternating double bonds. Check. Maybe positive, negative, lone pair. Don't have to worry about it because we already have alternating double bonds. Number of pi electrons. Can we write it as 4n plus 2? How many pi electrons does benzene have? Quick, hurry up. Give me a quick answer.
6.
6. 6. Can we write 6 as 4n plus 2? Then 4n equals 6 minus 2. That means 4 equals 4n. That means n equals 4 over 4 equals 1. Whole integer. Whole integer is good. Yes, aromatic. Okay. 115. That's not too bad. Let's write down this molecule. This molecule, the negative guy and the positive guy. Double bond, nothing here. Okay, let's go through them. Let's analyze the anion first. Cyclic, alternating double bond. Yes, there may be a problem down here, but then, well, let's look at the rules. No sigma wall. So it's not really a sigma wall because rule number 3 says positive charge or negative charge or lone pair may be okay. What does it have? Negative charge. It's okay. So let's keep going. Number of electrons. 1, 2, 3, 4, and count these two guys. 6. We already checked for 6. Aromatic. This guy. 1, 2, 3, 4. That's it. Nothing. 4. Bad idea. We saw what happens to 4. Not aromatic. Make sense? Let's draw this guy. Let's draw this molecule.
I have a quick question regarding that last one.
Absolutely.
So we wouldn't count like the positive charge on that for the amount.
Positive charge means there is nothing.
So
No extra electron. So you count, oh, down here, you count 2 plus 2 plus 0. There is 0 electron here. Positive charge means there is no electron. You rip that electron from here, wherever that is. Yeah, right there. So there used to be carbon had 4 electrons when this molecule was born. But unfortunately, when that happened, the hydrogen ran away with carbon's electrons. So it left with nothing. That's why it's a carbocation. That's why that carbon is positively charged, because now that carbon has an extra proton and a missing electron. Because the carbon lost this electron is gone with the hydrogen. That's why it's positive. Positive means no extra electron, you count 0. Make sense?
Yes, thank you.
Okay, so that guy is not aromatic. How about this molecule? How do you cyclic? Rule 1, alternating double bond. There is a problem maybe down here, but well, there is a lone pair. Okay, so rule number 4, 2 plus 2, you count the lone pair. One lone pair, only one lone pair, plus 2, 6. Yes, it's aromatic. Make sense? This is how you determine whether a molecule is aromatic or not. Okay, I'm going to keep this exam and the final very simple. In the, usually I go a little bit deeper, but I'm not going to do that. Okay, so as long as you can get through this process, I think you will be fine. So look at the board for a few seconds, and I'll take a picture of the board, and we will learn some names. Any questions so far? How many of you are there right now? On a Thursday, beautiful Thursday afternoon, 20. Okay. I'm trying to fake my feelings. This actually sounds like a good title for a chapter when I write my autobiography. I'm going to talk about these months as fake feelings. Okay. Cyclic, alternate double bonds, no sigma wall. Positive charge, negative charge may be okay. When you have a negative charge, you count 2. When you have a positive charge, you count nothing, 0. When you have lone pair or lone pairs, you only count 1 of the lone pairs. If you have this guy, maybe it's a good idea. I'm not going to take a picture. You remember it. It's going to be in the video. How many electrons, pi electrons does this guy have? 2, 4, 2 plus 2 plus 2, only 1. You count only 1, 6, not 8. It's not 8. Do not count both lone pairs. That's going to be a bad idea. You count only one of the two lone pairs. So if that's the number, aromatic. Okay? Erase. Time to erase. Let's learn some simple names. Very simple names. I'm going to keep the nomenclature very simple. If you really lose points for nomenclature of aromatic compounds, I will be very upset with you because I want you to get those points. Those are low-hanging fruits, okay? Simple names. And I will just keep them within whatever we have, within our territory, within our zone. If I haven't talked about some crazy molecule, then I will not teach you. I'm not going to be asking you about those names. I'm not going to put like a hydroxy group, OH group on a benzene ring and ask you to name it. That's unfair. I know that. But within the fair zone, I'm going to ask you some rules, some nomenclatures. Okay, you should be able to pull those off. Let's practice some names. Okay, so let's quickly erase the board. Nomenclature. Nomenclature is the fancy word for naming. Nomenclature of aromatic compounds. Okay, something simple. No need to freak out. Okay, the first aromatic compound you have seen is.
The screen's blurry.
Okay. Why does it do that? Because I'm moving around too much? Who knows? Okay, you know what? Let me just go back and deselect HD and select HD again. Maybe that'll do it. Okay. All right, that's benzene. I'm going to just teach you some simple and important molecules. Maybe you'll learn a few new functional groups. Okay. This guy with a CH3 group, what should we call it? How would you call it? If that's benzene and that's methyl, what should we call it? Quick. You should be able to do this. Anybody? A benzene molecule with a methyl group on one of the hydrogen's locations. What should we call it? Really? If you don't say it, I'm not going to talk about nomenclature, but I'll still ask these questions on Tuesday and Monday.
1-methylbenzene.
One is not important. Thank you for responding. One is not important because any location is one, right? You can move this guy. So yeah, we can call it methylbenzene. If you write that, thank you. I really appreciate it for stepping up. But there is a trivial name for it. You may have heard this name. You may have, I'm not sure. This is okay. This is okay. It's also called toluene. I want you to memorize it. Okay, it's called toluene. So if I have two methyl groups, how would you name it? Now you can apply your knowledge. This is Viviana. Viviana, can you name this? I'm not picking on you. It caused some problem in my organic class. I don't know what pissed off one of the students or some students. I'm not picking on you. I'm just, you don't have to answer, but then if you answer, I'll be grateful. Two methyl groups. Anybody knows how to name it? You have figured it out with alkanes, remember? How do you do it?
Dimethylbenzene.
Say that again.
Dimethylbenzene.
Perfect. Dimethylbenzene. Where are the methyl group? This is also dimethylbenzene. And this is also dimethylbenzene. Right? How do you distinguish between the three? 1, 2, 3, 4, 5, 6. So this is 1, 2. This will be 1, 3. And this will be 1, 4 dimethylbenzene. Pretty good. Okay. What would be the name of the slingshot with a big handle at the bottom? That's all I can think about. Whenever I see a Y, I think about slingshot. What's that slingshot called? 3 carbon, but not straight chain. It's an I word. Who remembers? Anybody? Who remembers?
Isopropyl.
Very good. Put it together. What should be the whole name? Like methylbenzene, you just say that and that. What is it? No trick. No.
Isopropylbenzene.
Yes. Sounds good to me. Let's do a few little weird ones. I'm going to hold off on that. You know what? We will name those in the last part, like teaching you some functional groups. Usually we teach the functional groups at the beginning. I like to teach the functional groups when we talk about carbonyl chemistry, which is the next discussion. Let's discuss them at the end. So let me see if I can think about some other simple ones. How would you name? Let's do one complicated one, then I'm going to teach you guys some chemistry of aromatic compounds, and that will pretty much be it. So let's do a simple one. Since you did isopropyl, how would you name this molecule? You know what? Let me draw the molecule like a kite. It brings back memories from my childhood. Kite with a tail. What's that guy called? Quick, hurry up.
Propylbenzene.
Fantastic. Propylbenzene. Let's do one a little complicated. Ready? Let's see if you can do it. I'm not going to give you much time. I'm going to give you 1 minute. So it's going to be some benzene. And there are two groups. Let's put a purple color on one, and let's put like a red color on the other. What are the groups called? What are the branches called? What's this branch called and what's that branch called?
Butyl and isobutyl.
Wow, man, you're on fire. That's butyl And that's isobutyl. That's very impressive. I'm not mocking you. Isobutyl, one word or two words?
One word.
Excellent. Isobutyl. You have to do yourself a favor by picking a second minor or minor in chemistry. That's an order. Okay. Finish it off. Which group should be named first?
Butyl.
Butyl. So it's going to be some number butyl, some number hyphen isobutyl, benzene. How do we number? Should we start numbering from here? Should we start numbering from here? Should we go the long way or the short way? I'm not going to say no, I'm not going to say it. I'm going to keep my mouth shut. I was going to say something that might not be received well. Shall I number it this way, 1, 2, 3, or shall I number it this way, 1, 2, 3? Green or blue?
With the butyl first, so from the order of butyl up to isobutyl.
Blue is wrong, green is right. Nomenclature done. Let's talk about some chemistry and let's break for the weekend. Let's party all by myself. You can invite yourself and me and I. There was actually a store in India where we worked for 5 years, me, myself, and I. I thought that sounded extremely selfish. Me, myself, and I. How much more selfish you can be? Yeah. Simple nomenclatures, okay? You should be able to handle it. I took a picture. I'm going to share it as soon as I can. Erase some reactions of benzene. So there are other compounds that don't look like benzene, but they can be aromatic compounds. But I don't think I'm going to be delving in those compounds. I'm not going to be choosing any of those compounds to torture you. It's going to be pretty much all the aromatic compounds are going to be based on benzene, or when I'm asking you aromatic or not aromatic, then I might put some weird structures. But for chemists, for naming and for reactions, it's going to be always a hexagon with 3 double bonds. Okay, that's FYI. So don't start worrying too much about things. So we're going to talk a little bit about same color. Okay. Reactions of aromatic compound, benzene. All right, so let's start with some bad reactions that don't work. Double bond, right? If you see a double bond, you might think, oh, it's a double bond, so it should react with bromine. If we take bromine, pretending that it's a double bonded compound, and if you expect bromine to stick to it, it doesn't happen. No reaction. Because it's stable. It's got that aromatic stability. It's a weird compound. That's why 1 to 3 chapters are completely dedicated to aromatic molecules in an organic textbook. Whether it's for majors or non-majors, it doesn't matter. We have at least 1 to 2 chapters dedicated for organic aromatic compounds because they're weird and they're weirdly stable. Stable means they're unreactive. So this reaction goes like nobody's business between an alkene and bromine. Doesn't work. Hydrogenation, remember we learned it in alkenes. You need to remember that for the finals. Okay, don't forget that. So when we did this chemistry, hydrogen gas, and remember platinum or palladium, you need to remember that as a catalyst. This reaction was called hydrogenation reaction. Remember saturation. You're filling in the holes. You have a double bond. You're filling it in with concrete. The concrete is hydrogen. You're making a single bond from double bond. Remember, you need to remember that from the past lectures, and if you want to read the book, whatever suits your style, make sure that you guys are on top of it during the break before the final happens. Okay, I'm going to be asking you again from those areas. Hydrogen gas, palladium and platinum on double bond, it goes like smooth butter. Doesn't work. HBr reaction, remember we talked about it? That's another reaction that we did. HBr or HI or HCl or HF, it just added to the double bond. No reaction. No reaction here. What works? You need to make that electrophile, that positively charged species, more positive, a stronger electrophile. How does it happen? Well, bromination happens. I'm just going to draw one of the double bonds because I'm going to just do the chemistry right here. Okay, the reactions that actually successfully happen, and the reaction that chemists have figured out. One reaction that goes pretty well is bromination in a funny way. You need to use the bromine with a catalyst. FeBr3, at this point, no point talking about the mechanism, memorize it. Iron and ferric tribromide, okay? This is a catalyst. CAT, cat means catalyst, not a cat, dog, cat, okay? What happens when you do that? Unlike in the alkenes, when both bromines get attached to the double bond, in this case, it's not an addition reaction. It's actually a substitution reaction. It's a weird reaction. One of the hydrogens, you know what? Maybe I should have written it in red color. Let me just write it down in red. So bromine and FeBr3, iron tribromide, this is catalyst. What happens? This only one hydrogen gets replaced by one bromine. It's a slightly strange reaction. Okay, the second hydrogen remains intact. This is replaced with the bromine. That's what happens. And it's got a name. I'll explain it in a second. So that's one reaction that goes on. Another interesting reaction that can happen, I'm going to use different colors. If you take benzene, and if you react it with sulfuric acid is pretty bad. H2SO4. Okay? If you use it with sulfuric acid, it actually produces, I'll tell you what, the electrophile that actually reacts looks like this, Br+. The electrophile that reacts here looks like this, HSO3 positive charge. Don't feel overwhelmed. You somehow have to figure out a way to remember it for the exam and for the final, okay? So that's the electrophile, and that just replaces one of the hydrogens. It is going to be a little more of You know, if you think that the course has been like a drizzle or like slow rain, it's going to be a little more flurry, some snowfall coming down from the sky. Okay, I'm not trying to scare you, but you need to step up and change your game plan a little bit. You have to spare a little more time right now to do well in the rest of this course. Please find the time. Beg your employer, ask your family to kind of step up and give you some cut you some break, okay? And this entire thing, whatever that electrophile looks like, that thing gets attached there, okay? SO3H. Another reaction that can happen is you take nitric acid and some strong acid as a catalyst, H plus as a catalyst. CAT cat period means catalyst. So what does that electrophile look like here? NO2 plus. That's the electrophile. What happens? Well, again, one of the 6 hydrogens gets replaced by that. So if you can think about it like a formula, and if you can remember these reagents and the electrophiles, it's going to be an easy game for you to conquer. But if you're confused about it and if you do not make any effort, it's going to be a disaster. The exam on Monday/Tuesday is going to have some chemistry from here. Whatever you're seeing on the board, okay, it's not going to be that difficult. So you need to remember some of this stuff. So please study. Almost done with the semester, okay? So just hang in there and study a little bit, and you should be able to pull it off. So that's the electrophile, and that's the reaction. And only one of the 6 hydrogens, I'm just drawing 2 because this is the happening place. Only one of the 3 double bonds actually does the reaction. That's that. One last reaction, I'm going to just teach you one reaction down here. And that reaction is going to be, if you take an alkyl halide, we have already seen it, so it's not too complicated for you. If we take an alkyl halide, or, you know what, let me just draw the alkyl halide in black and red. R X. That's the generic formula for alkyl halide. Let's put like an alkyl halide, like a real alkyl halide. An example would be ethyl, I don't know, ethyl bromide. Okay. Remember, it's got ethyl bromide has, or bromoethane has 2 carbons. 1 carbon here, CH3, CH2Br. It needs a catalyst, kind of like that, okay? And that catalyst is going to look like this: aluminum trichloride, AlCl3. Memorize, write it down on a piece of paper, stick it by your bed, by your dining table, memorize it. These 4 reactions. It's usually 5 reactions. I'm not going to teach the 5th reaction because we haven't really covered that kind of carbonyl chemistry yet. Alkyl halide plus aluminum trichloride. What does the electrophile look like here? That over here, it looks like a bromine with a positive charge. Over here, it looks like HSO3 with a positive charge. Over here, it looks like NO2 with a positive charge. Over here, when these 2 guys react, what do they produce? They produce a carbocation. It kind of looks like CH3, CH2, and a positive charge. That's going to be your electrophile. So that whole thing is going to replace one of the 6 hydrogens in this reaction. Okay, and I have been drawing this last double bond as a blue double bond. And so all you do is stick this guy with the positive charge, that electrophile over here. You need to watch this video probably 2 or 3 times to stick it in your brain. Seriously, I'm not kidding. So you make ethyl benzene here. It's pretty cool. So what do these reactions call? All these guys, this guy, this guy, this guy, and this guy, right? These four things, they are all electrophiles because they are electron loving. They themselves do not have enough electrons. 146, just hang in there for one more minute. Okay. All these guys are electrophiles. So this reaction, all these four reactions, they're called electrophilic. Electrophilic because an electrophile is involved in this business. Aromatic because you are dealing with an aromatic compound. Electrophilic, aromatic. It's not addition. You're kicking this guy out. This guy is going out and this guy is coming in. This guy is coming in. This guy is coming in and this guy is coming in. That's out and that's in. So it's not addition, it's substitution. Electrophilic aromatic substitution reaction. Okay. I don't think I'm going to discuss anything more on aromatic molecules. This is pretty much it. And I'm going to take a picture and we are pretty much done for the day. Sorry, I took a little extra time. Took a picture. I'm going to make the video available. It's not a whole lot of material if you do the minimum studying. I'm going to put the front camera. If you guys want to hang out for a few more seconds or minutes, I can be here and answer any questions. Who is still here? Viviana, Allison, Ivan, Angelus, Cassidy, Marley, Katrina, and Carlos. Did I miss anyone? Probably not.
I do have one quick question.
Absolutely. And this is Cassidy. How are you, Cassidy?
Good. How are you?
I'm all right. What's up?
So I know we do obviously have the final coming up within the next month, obviously. I know that obviously we've covered a lot of material. Are you going to provide any type of study guide, or are you going to provide, like, I don't know, anything to kind of get our minds back to the first couple chapters?
I don't think so, but in the past, I have always offered reviews, like that usually spans between 2 to 3 hours. I'll tell you why I don't have any more reviews. The first time when I had a review, per class, like 1.5 students showed up. And I was extremely disappointed, and what can I say? I'm trying not to be frustrated myself because I understand your pain. We have one in your house. He's 19 years old and he's going to college, like you guys. And we see him, so we have first-hand experience from the other side of the table, right? So we understand your pain. So I thought that since this is so different, since all the videos are available for you guys and everything is there, since you're asking, would you guys, okay, not many people are here, but maybe it's a good sample. 1, 2, 3, 4, 5, 6, 7 of you, okay? Allison, Ivan, Angelus, Cassidy, Vincent, Katrina, and Carlos. Would you guys be interested in having a review before the final? Would you prefer to?
Yeah.
Yeah?
Sure.
Will you actually show up and keep your
Yes.
cameras on? Because
I think
if you show up for the review and just don't turn on your cameras, it's going to be really frustrating for me.
I think it depends on, like, I think all of us, I mean, obviously we all have jobs and things, so we would need a week or two in advance just to clear that day. I wouldn't mind taking a day off work or anything to make sure that I'm prepared. As long as there's enough space for us to ask for time off. And it's not just like said that week, because then it's a little bit more difficult for us to get that time off.
Thank you, Cassidy. Anybody else? Any comments?
The same with me too, because I'm not always available. So if
Okay.
you let us know also beforehand, so I can take a day off or anything like that, would be really cool.
Okay, so there are 7 of you right now here. Would you guys think that a weekend will be better or not necessarily? So how about like, for example, Saturday, 7 a.m. to 9 a.m. Do you think in general, you guys know your fellow ChemEd students, maybe. I know that this is a weird semester. You probably haven't made any new friends yet. I know there is a chat. I'm not looking at the chat. If you're talking to each other, then it's fine.
I would be happy with it early morning because that actually would work.
If I take this group as a good sample, like for making an assumption for the whole class, do you think will it work for you guys? Will you prefer it Saturday 7 a.m. to 9 a.m. versus Friday, I don't know, 5 p.m. to 7 p.m.? Which one would you prefer? Can you guys give me some? Please don't reuse the chat. I'm not looking at the chat. Speak up, please.
I mean, for me, earlier works better just because my job starts at 3.
Any other comments? Saturday morning versus Friday evening.
Saturday morning.
Saturday morning. Katrina. Okay. Will you guys actually show up? I hope there will not be like 3 people, because that would be really very frustrating. That's why I'm not taking it out on you guys, it's nothing like that. And I'm trying to be as creative as possible, and it has backfired on me. I don't know. I think I realized that I didn't send that announcement specifically to my organic lab students. I accidentally sent it to everyone, and I didn't want you guys to read that, but it was too late. But something happened. Somebody went and complained to our chair that I was being condescending and I was putting people down when I was asking questions. Obviously, I'm making them work harder than the other instructors because I'm trying to teach them something. I think that you guys are paying money to come to school, not just to get grades, especially those who are going to be using this chemistry knowledge for all kinds of exams, MCAT and PCAT and DAT and whatnot, or some of you then will go to graduate school. So I'm trying to keep my conscience clear. I'm not trying to shower or bombard with homework, but I'm actually spending like 4 or 5 hours every week going over that. It completely backfired. I think some of the students were extremely unhappy and probably pissed off because I'm making them work harder. So they went and I think 1 or 2, I don't know how many, they went and complained to our chair, which is fine. And I'm not, I'm beyond that at this point. I've been doing it for quite some time. I'm not looking for pat on my back or, praiseworthy words, but I want at least 10 students to show up during the review. So out of 7 of you, you think you guys will be attending the review if I throw it and we announce it early enough? We can set it up maybe this week, whenever we want to have our review. Yeah, we can definitely set it up. I want you guys to have enough time so it'll be at least 5-6 days beforehand, so that you have enough to digest. And if you realize that, oops, shoot, I haven't studied that, you have plenty of time to catch up. So let's set it up sometime in the week, one of the weekends, okay?
Okay, thank you, Professor. I appreciate it.
No problem. Anything else? How many of you hate organic chemistry? If this is not your cup of tea, that's totally fine. You don't have to lie to me by saying that, oh, this is the best thing that has ever happened to me in my life. What do you think about this course in general? Any comments? Again, you don't have to please me. I want truth and honesty. Any comments? Since we are having like a friendly discussion.
I do think it's a little difficult for me.
Yeah. What's your major, Carlos?
Plant science major. Agriculture.
Okay, I'm sorry. Hopefully it'll be over soon, and hopefully you guys can. What could I have done differently to make your life better? If you ask somebody else and if you look at their notes from the past semesters, you will realize that the amount of material that's coming toward you, like a one-way street, is the concentration is much less this time. I'm not diluting it. I'm not making you feel bad. That's not the point. I deliberately decided to reduce the amount of materials. You will see that. Again, you don't have to thank me for that. That's the way the pace has been, and that's the amount of material I have transferred. So that's one thing. Usually we spend 2 to 3 lectures on aromatic chemistry and many other things. That's one thing, but I know it's difficult. I know that. If I go and sit in a physics class, I'll probably flunk. If I went to medical school, they would probably kick me out the same evening because I can't memorize. Organic chemistry is more conceptual, and I get that. But you don't, I know that it's not your thing, many of your things. So
I think overall it's actually easier than general chemistry for me personally,
I agree.
because general chemistry is just so much about so much. I think what makes this class hard is that I don't know, being online. I think, I mean, this is for me personally. I don't know if my peers can agree, but just being online for every class is really difficult to keep track of everything. And you do have those professors that honestly don't care to teach anymore. They just have given up. And it makes it really difficult as students who actually are here to learn, and we're actually trying to make something of our lives and chasing our goals, and kind of makes it difficult when teachers start to give up on you, because then it really puts you in a place where you're already doing it online and you're trying to keep track of that. Plus you're trying to fit it in with your schedule of work. And it makes it really difficult when you feel like you're not getting 100 when you're trying to give 100. So when you get that from a person you're supposed to be learning from, that makes your mindset switch a lot. Like it really does. I know for me, I was getting A's and B's all the last 2 years at Fresno State, and now I'm struggling to even keep my B's, and struggling now, and I'm getting more C's than I ever have, and that's really frustrating. Like, I really enjoy this class. I really enjoy you as a professor. I actually think you handle it really well, and you're always like making it interesting for us, and always have a good attitude, which I appreciate so much, because that makes me excited to get, learn. Even though it's organic chemistry, it makes me excited to like be in class rather than sit there and look at a PowerPoint, which I have my soils class. We do 60-page PowerPoints every day, and she just has no life to her, like nothing. And it's just like, you're sitting there and it's 8 a.m. and you're like, how am I supposed to be excited about soils if you're not? So
I hear you, Cassidy, and I appreciate it. I don't know if this is a general opinion in the class or you are one of the outliers in the class. That's exactly why I was, coming excited and showing up for my, like most of the other instructors in that organic lab, they show up only once a week. If I have my lab Monday and Wednesday, they were showing up only on Monday, and just kind of showing that these are the modules on Canvas. This is what you learn. This is what you do pre-lab and in-lab and post-lab. Submit them, and we will grade. Blah 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 blah. And that's the way we go. And I decided not to do that. I decided to I even go to my research lab and show them different lab setups, apparatus setups, but I don't really know because the chair didn't reveal the name. I don't want to know who actually complained, but she or he used the word we, like, like Dr. Maitra condescends us, like he puts us down. I don't know if she used the plural, on her own to make it more legitimate, or actually there are more people who actually are frustrated with me because I'm trying to teach them something. So I've been super frustrated. And that day was a bad day for me. I think I made some mistakes when I was setting up your exam. I think it was whenever that was Tuesday. I think Tuesday is when I came to know about that complaint. It's okay. I mean, I'm like, so I said that, sure, then let's go back to the module. I'm not going to teach you guys anything. I'm just going to do what others are doing. But now hearing it from you, I'm like, maybe I should be above all these small disturbances and keep doing what I actually truly believe in.
yeah, I think everybody definitely learns different. And I mean, you don't let one person overshadow how,
Yeah.
I mean, that's one person. I mean, I would say, because I enjoy learning from you. And yeah, there are days where it's hard, and there are days where there's frustration. I'm sure on your end,
Yeah.
you're frustrated, and we're frustrated. But overall, you're giving your actual time. You're setting up on a whiteboard. None of my other classes literally use a whiteboard. You're the only professor that I've had within the last 2 semesters that actually are using a whiteboard in teaching. So that makes so much of a difference. Like,
Cassidy, does it really make a difference for you guys?
Yeah. Are you kidding me? I would so much rather do this and be really into it and really focusing and learning rather than my professor sharing a PowerPoint. I mean, like that to me is like for a 65-page PowerPoint, just reading it off for an hour and a half, like not teaching. You know what I mean?
I'm gonna keep my mouth shut. I'm not gonna make any.
There's a
comment.
lot of professors, and that's what I'm saying. There's just professors that don't care to like actually get on their Zoom and teach. They'll just post modules, and that's fine. Like they're frustrated too. But I mean, think about how we feel. You know, we're
Yeah,
students.
No, I totally understand. And I also get it because we have been told by our higher administration. What's one thing that's nice about Fresno State is people are generally pretty nice and caring. Chemistry department is very caring. We care for you guys, not just me or others. I mean, everybody cares. All my faculty, even though I don't agree with them philosophically and I don't know, like philosophically and life goal and how we do our science, I may completely disagree, but generally everybody in this department cares for our students. Having said that, PowerPoint is, yeah, it's something that I don't like. I never use PowerPoint. I usually do what I do here. So it kind of strengthens my belief that what I do is the right thing, but then yeah, I don't know how I managed to make some students or one student extremely disgruntled and unhappy. Yeah, yeah, so that's that. Thank you for that. When you guys do your evaluation, I'm not expecting any fluff or praiseworthy words. You have nothing to gain from me. I have nothing to gain from you. I'm not looking forward to getting any promotion or any award, but I will appreciate some honest comments, maybe constructive comments. I'll appreciate that. Um, Thank you. Anything else? Anybody else? How are you guys doing in general life? I know that some of your lives are also like, turned upside down. With somebody said the children is staying home and parents lost job. So they're trying to step up and help. It's not easy. Otherwise, you guys can hang up or you don't have to listen to my rant.
Well,
Cassidy,
thank you for listening. I appreciate it.
thank you, Cassidy. What's your major, Cassidy?
Enology.
And what you want to do?
Open up my own minor.
There's a lot of chemistry in enology. You know that,
I know.
right? All the
P105.
really
Five
cool
next-
molecules, yeah. Antioxidants and the different color promoting compounds,
I
like
never thought I'd even be able to get through this class, and I'm just trying to push through it. So
you're doing fine so far. I haven't get to these.
yeah, I mean, it's been a little rough. I've done really well on one quiz. I did bad on one of the exams. I think it's just now I finally feel like I'm buckling a little bit. Like I need to really focus in, and
Please.
now I'm taking it, like a little bit more seriously than I think I was maybe a month or so ago.
It is changing from drizzle to rain to slow snowstorm rain.
Khan Academy has become my best friend within the last like month. So
All right.
all right, thank you.
Thank you so much. Have a good weekend. Take care. Bye, Carlos. Bye, Angeles. Angeles, do you have any questions or any comments? No?
I was just listening to the conversation, but Cassidy basically said what I wanted to say. So
Thank you. Appreciate that. Any feedback, any constructive feedback is always welcome. Okay. Bye, guys.
Thank you. Bye.
Carlos, take care, okay? Let me know
You
if
too.
you want to set up some office hours. I really do not mind spending more time with you guys. It's going to be fun. I like talking about chemistry, so I would love to go over some stuff in the weekends, set up a Zoom meeting. So just let me know, man. You need to reach out. Otherwise, how do I know? I mean, what do you guys need? I really don't mind going over it 10 times. I will feel better about my life and breathing oxygen that way. Sincerely, please. So keep that in mind, okay?
Okay, thank you.
All right, man. Take care. Have a good weekend.
Have a good weekend.
Get some rest. Bye, Angeles. Anything else, or you're good?
I'm good so far. Thank you.
Bye. Take care. Okay. Bye.
Bye.